not enough.
How many more labs do we have, by the way?
I don't
I don't know either.
All right. We have so much in common.
6 labs left?
You're
joking.
We can make it 6 if you want.
Please, God.
Sir?
More tests.
The labs are literally my least favorite thing.
Yeah, no.
I love the labs.
I'm never good at
It's probably because
That's someone does.
It's okay, I like the labs too.
Now, harmonic motion.
harmonic motion.
Simple harmonic motion.
what does simple mean again in this case?
All right, first let me write it down. Simple harmonic motion, often abbreviated as just SHM. The simple means that it is, in essence, frictionless.
What about harmonic?
Harmonic, repetitive, adjective, and motion. So once it starts in this repetitive motion, it's going to go on forever. That's the simplicity of it. Now things in simple harmonic motion obey Hooke's law.
So, simple harmonic motion you just said keeps going on forever?
Yep. There is, and that which doesn't is often called damped harmonic motion. We will not get into that, but damped harmonic motion.
With a P.
D-A-M-P-E-D.
Okay, so like dampen.
Hooke's law, negative Fk delta x. And your lab started out with this formula right here, that the force that a spring, an ideal spring exerts is proportional to, but in the opposite direction of the displacement. So if I have a slinky, which I saw one around, oh, there's a slinky right there. So if I have a slinky, if I pull it down, the force the spring exerts is up. So the displacement from equilibrium is opposite the direction of the force that the spring applies. If I push up, the spring is pushing down. I know that F equals ma. So if the only force, if I attach a mass to that spring, if the only force attached to that spring is the force due to gravity of the spring itself, let's actually simplify it. Let's make it on a horizontal frictionless floor. So I've got a spring here. We'll call that equilibrium right there. And then I stretch it out with a mass attached to it. So the mass will have a weight and a normal force, which will balance each other out. The only force that is accelerating it is the spring force. So that would be equal to the mass of the object times its acceleration. We know, yes, all of us do, that acceleration is the change in velocity over the change in time. And we know that velocity is the change in position over the change in time. So acceleration, therefore, would be the change over change in time of the change in position over the change in time. Or in pseudo math notation, delta squared x. If you had calculus, you'll see where this is coming from. If you haven't had calculus, just sort of roll with it. I need some function that's going to relate back to itself. I know that velocity is the slope. This is, if I think of this, if I have a position time graph, this velocity is the slope. If I have a velocity time graph, the slope is acceleration. So I need some function so that the slope of that function gets us back to something that looks kind of like position. Since acceleration is the slope of position, and I got position here.
Why did you just put a delta on A with the acceleration?
Wait, sorry, what? Oh, that,
Yeah.
because it's the change in that. I guess I could have also written it as delta over delta t, and then the numerator written delta x.
Okay, thank you.
So I need a function whose slope of it looks like the original. Now, you might also be looking at this and see a delta x there, and I have just an x there. Let's resolve that. I did something with the pen, of course. Put it over here. I have negative k x final, this x minus some initial position, its equilibrium position, is equal to mass times acceleration. Negative kx plus kx sub naught is equal to mass times acceleration. That's just a constant. It has some initial position, and k is the spring constant. I can simplify this greatly just by saying, you know what, let's just make equilibrium position 0. Because I can make 0 wherever I want. So if I let x sub naught equal 0, then this just becomes negative kx. It's mass times acceleration. So what function can I do the slope of and get something very similar? Well, one solution. If I have something that looks like this, let's take a look at the slope.
Is x sub 0 the same as x sub I?
Yes.
Yeah, pretty much. In this context, x sub 0 is, you are sort of setting x sub 0 to be the equilibrium position.
So for,
It doesn't have to be, but just, it's
It's simpler to
simplistic
do
just
so?
think of it that way.
Okay.
like on a quiz or a test, would you want us to identify that?
No.
Okay.
And you would only identify it if it weren't. All right, so if I looked at the slope of this, I don't want it there, I want it there. Where is the slope of this equal to 0? So if this is x and time,
At the points where it crosses the axis?
go.
What was the question?
Oh, at the crust and troughs?
Yeah. All right, so there, and there. By the way, this is just this is actually a cosine curve, x equals cosine of t. So that would make that 2 pi, that's pi. In this first region right here, positive or negative slope?
Which region?
This region right here.
Negative,
And then in this second region,
positive.
this is a negative sine curve. So since that's position, this is velocity. Velocity is equal to negative sine of t. If I did the slope of this, where's this equal to 0? Where's the slope equal to 0?
At the same point, like at the bottom of the curve and the top.
Okay, peaks and troughs. In this first region, it's negative, and then positive, and then negative again. So this would be acceleration is negative cosine of t. So cosine curve works. If we kept going, there's actually a cycle there. If I start out with a cosine curve, the slope is going to be a negative sine curve. The slope of that will be a negative cosine curve. The slope of that is going to be a sine curve. The slope of that is a cosine curve, and it cycles through. Now, this is all well and good, but functions have more than just a single thing, a single trig function here. I get a cosine of 2t. If I put a 2 there, what would that do to my graph? What would it, if I stuck a 2 there, what does that do to this graph? From the hand gesture back there, it shrinks it. So, just go to the page.
Remember correctly, it's increasing the period is the term.
Say it again?
It's increasing the period, I think is the term.
Decrease, you said decreases?
Increasing.
Increasing the period. It's happening more frequently. I think that's.
Yeah, so that would decrease the period. Because it takes less time.
Oh, yeah, okay.
So if I had, x is equal to the cosine of 2t, then from 0 to 2 pi, it's gonna do 2 cycles. What does that do to the slope? That was badly done.
It increases it.
Yeah, if I have something that looks like this and then I cram it into less space, less horizontal space, it's gonna make it steeper. And so what's gonna happen here is that I still get the negative sign like I did before, except that number pops out front, makes it twice as steep. Negative, wrong letters? Negative 2 sine of 2t. And then if I did it again, I'm gonna, from sine, I'm gonna get, or negative sine, I'm gonna get negative cosine, that stays the same, but then that pops out again.
Is that an A or an alpha?
That is an A. Negative 4 cosine of 2t. So if I'm just sticking the 2 there, basically makes my acceleration 4 times greater. If you think about another way of looking at this, if I have a wheel here spinning about its center, and I have a pole, like a peg sticking out here, I have a light source from above. If this thing is rotating around like this at some angular speed, you're going to see his shadow move back and forth like this. If I double the angular speed, this is going to move twice as fast, which means this is going to move back and forth twice as many times. And the time it takes for that to go around once, well, it'll go around once in half the time. So where period was 2 pi, the period is now pi. One other thing, and then we'll do some vocab words here. If I did x is equal to 2 cosine of 2t, what does that 2 do?
That increases the, well, that's just the amplitude.
Yeah. What's that do to the slope?
Determines how high or low it goes.
Yeah, in terms of, is that going to make the slope bigger or smaller?
Correct me if I'm wrong, but it doesn't really matter.
It does matter.
Then it would be bigger.
Yes, it is bigger. Because instead of having a graph that looks like this, I now have a graph that looks like this.
Oh my god.
Where it's 0, it's still 0. 2 times 0 being 0. At least that's what the math people tell us. But since I have a larger swing, I've got a greater slope here, so that somehow has to get taken into account. And so that just stays out there the whole time. And so and I'm going to change this to a 3 because
Why?
I have 2 different 2's there, and I want to make it clear which 2 is which, or what is the effect of this versus the effect of that.
Well, you just erased the last 2, so why don't you change that?
So if that's 3 and 2, then from cosine I'm going to get negative sine. That still holds true. That's still going to be 2t. That doesn't change. If I have this wheel spinning, I'm not changing the rate it's spinning. All I'm doing is changing how big the wheel is. And then it's going to be 6. I got the 3 hanging out front times the 2 that I bring out. My acceleration is also going to be negative cosine. That doesn't change. It's still 2t, but when I go down to the slope, that 2 right there multiplies, and so I get negative 12. The calculus is known as the chain rule.
The what?
Chain
Chain rule.
All right, vocab. Here, omega is the angular speed of the wheel. If I stick it here, though, if I go just the generic formula of x is equal to some amplitude times the cosine of omega t, this omega is known as the angular frequency. Now, what's the difference between angular speed and angular frequency? They have the same symbol, omega. They have the same units, radians per second. There's a philosophical difference, but in terms of math, I can't think of any situation, nor have I thought of a situation in the past decade where really you need to know much difference between them. This is the amplitude. This is the phase shift. Because if I start a spring, if I start this oscillating up and down, did I start it when it was at its peak? At what point do I start the stopwatch? Well, in the lab that you did,
10.
What?
They were 10. We stopped the stopwatch on
No, he's saying when do you start?
when do you start the stopwatch?
when it's the most stretched out.
Ideally. But if I'm just looking at I got this thing oscillating, and now you start the stopwatch, or you might try to start it at this point right here, but you might miss. This phase shift is just telling you, basically it shifts the graph left or right in time, and it allows you don't have to start it at 0. You don't have to start it at the peak or at the equilibrium position. And D is just a vertical shift. So if I have this thing oscillating back and forth, and I want to know what the position is, if I set position is equal to 0 at the ground, then D is not 0. D would have to account for how far it starts out above the ground. Typically, if you let x equal 0 at the equilibrium point, D is going to be 0. If you start it when it's at its peak, or the most extreme, phi is 0. And that's generally the way 151 works, but not always.
Do you want it to be most stretched out at some point above the ground so that you're sure it's most stretched out?
So usually it will be most stretched out at some point. If it's
Do you
not
wanna
most stretched
start-
out at some point,
Do
then
you
it's
want
not.
to hold it high enough above the ground that it can be most stretched out somewhere above here?
Oh, yeah,
Okay.
yeah. Because then you're introducing another force into the problem.
Like,
So, given what we've just talked about, let's plug into our formula over there that negative kx equals ma. So negative kx is equal to ma. So I have negative k. X is, let's assume that we start time at an extreme, so phi is 0. Let's assume equilibrium is x is equal to 0. And so we have a cosine of omega t is equal to the mass times, well, acceleration is the slope of the slope. So I have negative a omega squared cosine of omega t. Because when I do the slope, omega pops out, and I do the slope again, I get another omega, so it's omega squared.
so, what does V equal again?
V,
Velocity or speed?
the velocity,
In
yeah,
term-
that slot moves my vectors.
In terms of, like, trig functions?
Yeah, so if my position is described by a cosine omega t, my velocity is described, modeled by a omega, negative a omega sine omega t. And my acceleration, negative a omega squared cosine omega t.
Let's go back to the blue. The question, this is all making sense.
Do you always have to include phi and d in the effect?
For most of the problems that we're gonna do, they're gonna be 0. All right, the negative signs cancel out, the amplitude cancels out, cosine cancels out.
So basically, the whole problem goes away?
No, we have left with k is equal to m omega squared,
Okay.
which means that k over m is equal to omega squared. Which means that omega, my angular frequency, is going to be whatever the spring constant is divided by the mass.
Yeah. Which we are allowed.
They're gonna go a step further, because you did measurement of time, you were finding period, what's the relationship between period and angular
Is
frequency?
it on the sheet? No, that one's not on the sheet. Maybe it is on the sheet. Yeah, this equation is not probably on the sheet. Yeah.
So angular frequency has units of radians per second. Regular frequency is oscillations per second. It's how often something happens, so it happens 5 times a second, 7 times a second, these are frequencies. So frequency, if I think about the wheel that's going around like this with some angular speed, there's an angular frequency there, but the shadow moves with a certain frequency, an angular frequency. The relationship between the two is a factor of 2 pi. And so omega is 2 pi times the regular frequency.